So my project is on the socio-economic and cognitive determinants of biochar implementation in tropical land management, which is a case study from my internship in rural Costa Rica with BaumInvest. So first, I want to understand the global and local context of soil degradation and how it impacts our environment. Degraded soils have released 78 gigatons of carbon into the atmosphere, which has contributed to atmospheric CO2 levels surpassing 420 parts per million, which is an alarming rise linked to global warming and climate instability. Compounding this issue, 75% of Earth's surface is degraded, which has impacted the livelihoods of over 3.2 billion people. If current trends continue, by 2050, 95% of land will be degraded, and it will threaten food security, biodiversity, and amplify carbon emissions. Taking a closer look at the context in Costa Rica, here the challenges of soil health and carbon emissions are magnified by extensive pineapple monocultures, and these systems have caused severe soil degradation, leaving the land heavily reliant on chemical fertilizers, which has impacted farmer livelihoods. This is a problem that has gained a lot of public attention, as you can see on the slide. There's an image of a protest, and the banner says, "Yes to life, no to pineapple plantations." Despite these challenges, Costa Rica is a pioneer in sustainability. The country's ambitious goal of achieving carbon neutrality by 2050 is supported by initiatives like the Payment for Ecosystem Services program, which encourages sustainable land management. With all that in mind, biochar has emerged as a pioneer solution to some of the environmental challenges that we face today. At its core, biochar is a carbon-rich material that is produced by heating organic waste like agricultural residues and forestry trimmings in a low oxygen environment, often via a process called pyrolysis. This process transforms biomass into a material that's highly porous and chemically stable, making it a unique tool for managing waste and enhancing soil properties. In recent years, it has gained a lot of attention in the environmental sector for its potential to address modern issues like soil degradation and climbing carbon emissions. Studies show that biochar has a wide range of benefits, particularly for tropical soils like those in Costa Rica. It has been shown to improve water retention in degraded soils and raise soil pH, which neutralizes acidity, which is crucial for areas affected by monoculture farming. Biochar also enhances fertilizer efficiency by retaining nutrients like nitrogen and phosphorus, and this reduces fertilizer use and could lower nitrogen leaching by up to 50%. One of biochar's most significant contributions is its ability to sequester carbon. By locking it into a stable form, it can remain in soils for hundreds of years, making it a key tool to address climate change. There have been a number of studies looking at barriers to implementation in other regions of the world. One of the most significant barriers that these studies picks up on is knowledge. Farmers often lack information on biochar and its benefits, which slows implementation. As the chart on the screen shows, it's done by a study in Tanzania by Rogers, and it illustrates that knowledge was the most frequently cited barrier to adoption, with the majority of respondents agreeing that it prevents wider implementation. Cost is another critical obstacle. High initial investment requirements, as noted in various studies, makes biochar inaccessible to a lot of farmers. And then finally, research on kiln design highlights that while low-cost methods like the Kontiki kiln I'll use in this study are accessible, they often result in inconsistencies in biochar quality. So a study looking at the feasibility of biochar implementation hasn't been done in Costa Rica, which is the gap that my research is aiming to fill. And I aim to do that with three objectives. First, to identify factors influencing farmers' willingness to use biochar. Second, to evaluate the feasibility of low-tech biochar production for carbon sequestration and agricultural improvement. And third, to integrate the two, a technical analysis through a biochar trial and a statistical analysis through farmer surveys to assess the viability of biochar practices. My hypothesis is that the implementation of biochar among Costa Rican farmers is primarily influenced by three factors. First, their level of awareness, their financial incentives, and then their access to technical knowledge. So my methods will be a two-part methods. I'm first going to go over the biochar trial, and then I'll get into the statistics and the survey. So for my biochar trial, I made biochar using a Kontiki kiln, and the trial took place in June at the start of the rainy season in Costa Rica. For this trial, I used two types of biomass. The first was Voitschizia guatemalensis, which is sebo, and the second is Voitschizia ferruginea, or Bacteremma. After production, the biochar was analyzed at Tech University by Dr. Moya, and he analyzed it for carbon, hydrogen, oxygen, nitrogen, sulfur, ash, and volatile levels. And this trial provided a valuable insight into the practicality of low-tech methods and the quality that they could produce, laying the foundation for the second part of my research, which was the biochar survey that I conducted. Due to the absence of primary data on farmers' perceptions and willingness to adopt biochar in Costa Rica, I developed and conducted a survey to collect secondary data on the topic, and I aim to assess it with these key areas. First, demographics, so the farm size, their education level, and the farmer age. Second, their land use practices, so if they participated in the PES program, the crops they produced and the fertilizers they used. Third, their waste management, so how much waste they were producing, what kind of waste it was, and how they disposed of it. And fourth, their biochar awareness, so their familiarity with biochar, their likelihood of using or producing it, and their objectives, so why were they interested in using it? And then I looked at economic feasibility, including their willingness to pay for biochar, and any anticipated barriers that they might have to adopting it. The survey included 40 farmers, and it was selected through convenience sampling. The survey was conducted in person via phone calls and online to ensure flexibility in reaching as many participants as possible. Privacy and voluntary participation were upheld throughout the survey, and the map on the screen highlights the most represented provinces, which were Heredia and Aloeja. The data was cleaned using RStudio, and I employed two statistical methods. The first is a logistic regression to identify the key factors that were impacting biochar adoption, and the second was the multiple correspondence analysis to explore relationships between categorical variables. Next, I'm going to get into the results. So again, I'll do the biochar trial, and then I'll get into the survey results. So for the trial, both sebo and Bacteremma met carbon benchmarks for soil-enhancing biochar, with carbon contents of 85% and 82% respectively, which is well within the typical goal range of 70 to 90%. However, there were some limitations. Both species produced high ash and volatile contents, which highlights challenges with the open-air kiln design. And another key takeaway was that biochar did have low hydrogen and sulfur levels, ensuring its stability for soil application. Overall, the trial demonstrated that low-tech methods like the Kon-Tiki kiln could be feasible for biochar production that will act as a soil amendment and sequester carbon. However, further refinement is needed to improve consistency and quality, particularly for farmers that are looking to sell biochar or to participate in carbon credit programs. These are the key survey takeaways. There were 39 valid survey entries in the end. Most respondents were involved in crop production at 68%, followed by animal farming and forestry. 66% of the participants managed small farms of less than 10 hectares. And in terms of biochar awareness, 68% had no prior knowledge of biochar, which aligns with the graph on the left, showing that 42% of participants cited knowledge as the biggest barrier to adoption. This finding is consistent with current literature as well. Other barriers highlighted in the graph include results like resource constraints at 24%, equipment constraints at 17%, which further underscores the need for practical support alongside knowledge dissemination. Looking at the interest, 53% of respondents said that they were interested in using biochar for fertilization, while 42% indicated that they were interested in using it for carbon sequestration, though I should note the people who said they were interested in using biochar for carbon sequestration were also interested in using it for fertilization. And 16% were neutral on the topic. Through the in-person and phone call interviews, I kind of gathered that a lot of people were unsure of what sequestration was and why it applied to them. This is the logistic regression results. One significant finding was that prior knowledge of biochar was strongly correlated with education levels, so suggesting that farmers with higher education were more likely to know about biochar. Another key takeaway is that farmers producing biochar waste, specifically wood, were more likely to have larger farms. So this suggests that forestry and agroforestry farms are more likely to be larger, meaning that they have more access to materials needed to make large amounts of biochar, making it potentially a more feasible option for these farmers. This slide is the multiple correspondence analysis. So again, this is a tool used to explore relationships between categorical variables. Dimension 1, shown on the x-axis, captures the primary contrast between objectives like biochar for use for carbon sequestration or using biochar as a fertilizer, and the likelihood of farmers implementing biochar. And then the second dimension, shown on the y-axis, shows how certain categories, such as barriers, are distinct from other categories. A key finding is this separation of barriers in the top left that indicates that while barriers is a significant category, it's weakly correlated with other factors such as objectives or likelihood to adopt biochar. Conversely, in the bottom right, this cluster shows strong alignment between objectives and likelihood of implementing biochar. And then the neutral factors in the middle, such as the current size of the farm and the current fertilizer use, cluster centrally, which means they show less influence on dimensions, but they still contribute to the broader context of the survey. The biochar trial and survey revealed key barriers and opportunities for implementation. Low awareness was the main challenge alongside resource dissemination, alongside knowledge and resource and equipment challenges, highlighting the need for accessible solutions. The trial demonstrated that low-tech methods like the Kontiki kiln can produce biochar with strong carbon content and long-term stability, but they require process refinements to improve consistency and quality. MCA results showed alignment between the goals like fertilizer use and carbon sequestration, with the adoption likelihood, emphasizing that addressing barriers like education and resources could unlock biochar's full potential for soil health, agricultural productivity, and climate change mitigation. To address these barriers and capitalize off the opportunities, I propose several recommendations. First, education is key. Tailored training programs can increase awareness and equip farmers with the knowledge they need to implement biochar effectively. Second, cooperative access to equipment, such as shared Kontiki kilns, can lower upfront costs. Financial incentives are also really critical. Subsidizing biochar, possibly through carbon certification initiatives like the one offered by Vera, could make this practice more accessible and appealing to farmers. And then lastly, partnerships with local organizations and NGOs can help scale these efforts and provide infrastructure needed to ensure long-term success. Future research should focus on optimizing low-tech pyrolysis methods, conducting larger studies, and evaluating biochar's long-term impacts on soil health, carbon sequestration, and most importantly, farmer livelihoods. With the right support, biochar can be a transformative tool for sustainable agriculture and climate mitigation. And these are my references. And then I don't think I have time to fully read my acknowledgements, so I just want to say a big thank you to everybody who helped me with this project.
Thank you. Great job. I think Michael is online. Would you like to ask a question? Michael? Or maybe for now we'll go to Rasoul. I'll just the mic over to you. 1 second.
Thanks, Erica. Great job. It was not easy staying in Costa Rica, doing all of that work. I appreciate that. So your work is very comprehensive. You have biochar production, you have data about the feasibility of the biochar production on the site, and you have the survey about scaling up the biochar, at least at the local condition. So you say that it could be a transformative approach for the carbon mitigation. Maybe let's say if you go back to Costa Rica, not that I want to send you back, but if you are hired by the company to manage agroforestry or plantation site over there, how would you approach this in practice really to implement that? Do you think with the survey knowledge that you have now, it is promising to go for this direction? Especially we have seen that it is not just us, there were other farms in other locations in Costa Rica. They have already started to do this as well. So what do you think about that?
I think in order to make biochar production sustainable, it needs to be a group effort. BaumInvest, for example, was able to use their forestry trimmings, but a lot of other farms didn't have necessarily a lot of waste, especially most of the farms that were under 10 hectares. I can give you an example of a large-scale biochar project. I'm not sure if this really answers your question, but Vera has their first certified project, and they are banding together 5,000 farmers for this project in India. And I think that, like, I am pro low-tech methods, so I think doing it really simply and producing a lot of it with a big group of people would be the best way to make biochar that will sustain production and make it cost-effective, especially in a rural and lower income setting like Costa Rica. Yeah, did that answer your question?
Yes, of course. And I think you have the answer to the next question here in Vera. In case you want to prove for Vera that it has additional value for carbon sequestration, how the procedure would look like to propose to the community that they can benefit from that. Can you explain about the carbon certification process of the biochar a little bit?
Yeah. There are lots of steps to certification. First, you need to come up with a project design plan and get it approved by Vera. To do that, you need to have all of your details. You need to have already tried to make biochar and have a distinct plan for how you will make biochar. And there are a lot of criteria that you need to meet. Luckily, organizations like Vera allow low-tech biochar they make assumptions for you, and an external evaluator comes to the site and makes sure that you're doing everything correctly, but they also let you fill a lot of gaps. Like if you are not measuring the temperature, they'll assume your temperature. And they'll also assume the amount of methane that you're producing if you're using low-tech methods, which makes it more accessible to communities like the one in India, who's doing it through solar or pit kilns covered in steel shields. And then once you get approved, you get posted online, and the public and stakeholders can comment on it. And then you make necessary adjustments after that period. I think that they just got approved this year for the project, but it took them a full year to go through the complete process. So it is kind of a long and grueling process. Yeah, but once you are approved and an external evaluator has approved it, then eventually you'll get into the crediting period and you can produce biochar with an assumed amount of sequestration. If you kind of make a promise for the amount of biochar and amount of carbon you sequester, and then you work to meet that, and you hopefully get renewed.
Okay, great. Based upon, let's say you have Vera, it is approved, you have the project going on. Of course, you get some payments for the carbon credits on your side, or you can offset some of the emissions that you have. Now, my question is just hypothetical. If they succeed to do so, how much do you think it will change the land use in the area? Can this additional economic benefit kind of solve some parts of that pineapple plantations, cacao plantations, coffee plantations, citrus plantations?
I think it would definitely improve soil quality, because if you're producing that much biochar, you're also applying it to the soil. Vera in particular has a rule that you have to apply it within 1 year of producing it. Yeah, I think it would probably bring economic success to a lot of poor, more soil degraded regions. However, I do think that the effects may not be gigantic. A lot of the people that I talked to were already composting, so it wouldn't really impact the way that they're getting rid of their waste. They're still keeping it on the property and finding a different way to use it. Yeah.
Okay, any